All right, Mr. Jones here. Doing AP Chemistry Notes, pages 55 and 56. We're going to focus on what's called Kp, which is here. Now the P just means that we're focusing on pressures. So here, I mention here the book doesn't bother putting the little p. It's because they have dedicated the entire chapter to this concept. So they didn't feel the need to, but we're going to be covering Kp for pressures and Kc for concentration and any other generic equilibrium. So I want us to put it. So if you take a look at this example here, Kp is going to be products over reactants. So in this fictional reaction, my product chemical B is here, a reactant chemical A. And when you're doing pressures, please put a P in your expression to emphasize that it's pressure. Also, put it in parentheses and not brackets, because as I mentioned over here, brackets mean molarity at equilibrium. So it's a specific situation. So in this case, it's not molarity. So do parentheses and put the P to mean pressure. And you raise the chemicals to their coefficients, which in this case would be little b and little a here. But we'll see that in future problems. Now, typically the pressure will be given in atmospheres. I suppose you could do it in other units as long as all the units are the same. And it is dependent on temperature, the value of the equilibrium constant, like most equilibrium constants are. Moving along here. There actually is a way to compare Kc for concentration and Kp for pressure of the exact same reaction. So it's no surprise we go to the ideal gas law. If you solve for pressure, you get the second version. And then notice we can replace P with Kp, and we can replace the moles over V with Kc because that's molarity, especially if R has liters for its volume. And we now get this situation here. Kp equals Kc times RT raised to the delta Ng. So the Kp, the Kc, and the RT came right from replacing these items with these two items. And the delta Ng up here adjusts for how many moles of gas are in the reactants and products. So as I mentioned here, it is the change in the gas moles. Now I mentioned some stuff in red here about the Haber process, which we've mentioned before. And if we have time, I can do this demo regarding smog and dinitrogen tetroxide and nitrogen dioxide. I don't really want to take the time to work on that right now, but we will discuss this more in class with the equilibrium of the Haber reaction. Right now, I want to focus on this delta Ng situation. So what you do is you look at how many moles of gas are in the product and how many moles of gas are in the reactant. So in this first example, there are 2 in the product, 1 in the reactant. So 2 minus 1 is 1. In the second, the Haber reaction, we've got 2 in the product, and then we have a 3 plus 1 in the reactant. So 4 minus 2 is negative 2. And in the last case, it's equal. 2 in the product here, and 2 in the reactant. So in this case, it's a 0. And notice, based on the equation above, If delta Ng is a 0, then this entire thing is eliminated, and now Kp equals Kc. They're the same value. Because try to remember what an equilibrium constant is. It is simply a certain amount of product divided by the amount of reactant. It is telling you where the equilibrium lies between the amount of product and the amount of reactant. So in the case of the situation where delta Ng equals 0, the amount of product versus the amount of reactant is the same regardless of whether it's concentration or pressure. All right, next example. We have a temperature here, 300 Celsius. It gives us the Kc, and you need to pay attention to that now, that it's 9.5 and that it's a C for concentration. We want the Kp. So delta Ng, we've already figured out that it's a -2 from the prior example, so you just plug it in the equation. Kp equals Kc, R, T in Kelvin, because we have the normal R, raised to the delta Ng, and you get 4.3 times 10 to the -3. And in this case, the Kc ends up being 9.5, but the Kp ends up being 4.3 times 10 to the -3. And what that's saying is, based on pressure, this reaction does not really like going forwards. In fact, it'd prefer to go backwards. And since these are gases, pressure is an important factor here. And this actually is part of the reason why this is an interesting reaction. It doesn't prefer to go forwards when the chemicals are in their gas state. All right, next example. Similar situation. You're given temperature, you're given a Kc. We're solving for Kp, so you plug in the Kc, R, T in Kelvin. In this case, delta Ng equals 1. And in this case, you get an answer of 0.11. And again, this equation just allows us to convert between Kp and Kc. Now, where you need to be careful is certain problems will be tricky. They'll talk about all the chemicals, and they'll talk about their concentration, the concentration of this and the concentration of that. But then they'll give you the Kp. And if you don't pay attention, you will use the concentrations in the Kp expression. And what you need to do is either convert your Kp to Kc so that it matches the concentrations that were given, or convert your concentrations into pressures so that it works with the Kp. So be aware of that and be careful. It will come up a few times. All right, next. As it mentions in the notes, and I kind of mentioned this earlier, the book mainly focuses on Kp, if not entirely. We will be dealing with both Kp and Kc. So again, pressure here. Concentration here. We're going to do both at the same time. So now you see a note that I mentioned. I said, when manipulating reactions, it will be different than Hess law. Now, Hess law was really nice. Hess law basically said, whatever you do to a reaction, you do the same thing to the delta H. So you double a reaction, you double the delta H, you reverse a reaction, you make delta H negative, and so on. When it comes to equilibrium constants, you don't do the same thing. You do something more severe with the math. So I came up with a word for this. The word I came up with is here. You mathicize it. So in the case of equilibrium constants, Whatever you do to a reaction, you do the more extreme math to the constant. So take this first one, the reciprocal rule. If you reverse a reaction, you don't make your K negative. That wouldn't make any sense to have a negative K. You inverse it. If you change coefficients, for example, if I balance a reaction with whole numbers and you balance a reaction with numbers that are half of my whole numbers, neither of us are wrong, but our K values don't match up. So whoever has the lower, or let's say half of the other person, we would take the square root. Let me say that again. If a balanced reaction, if you cut the coefficients in half, you square root the equilibrium constant. If you double the coefficients, you square the constant. And so take this example here. We start with this version, and then we cut it in half. So notice 1 to 1/2, 2 to 1, and 2 to 1. Because the coefficients were cut in half, we will take the square root of the K value, whether it's a KP, KC, KA, KF, whatever it happens to be, and we get 8.7 in this case. Now, because of this, right now in this unit, if a person balances a reaction a certain way, like this first version here, and another person balances it a different way, like here, you'll get different answers to different calculations. So you'll notice the problems will often say the particular reaction happens and this chemical has a coefficient of 1. And by saying that, it is forcing everybody to put the same coefficients so that we all use the K value correctly. And you'll see that in the problems that we do. Now here, I want to talk about what if you have multiple reactions involved. Again, with Hess law, you would just add the reactions and you would add the delta H's. Here, things are more extreme. Let's say we take 3 reactions, 1, 2, and 3, and we add them together to get something called reaction 4. You don't add the K's, you multiply the K's. So K1 times K2 times K3 would equal K4. So take this example with phosphoric acid. Phosphoric acid will lose its hydrogens in different amounts. So you have reaction 1, or the amount of hydrogen that is lost from the original acid. Then you have reaction 2 for the amount of hydrogen that is lost from the dihydrogen phosphate. And then you have reaction 3 for the amount of hydrogen that's lost from the hydrogen phosphate. If you add these 3 equations together, you get what I have called reaction total, or reaction 4. Then you end up with this scenario as written. H3PO4 is in equilibrium with 3 hydrogens and phosphate. What I'm trying to show here is if you write the K expression for each reaction, so first reaction here, second reaction here, and third reaction here, if you add these together, the K expressions for reaction 1, 2, and 3, you do not get the K reaction for the total. But if you multiply them, you end up canceling here and here, here and here, and you end up with this expression, which matches what we would have gotten if we just wrote the K expression for this right here. We would have written that, and they match. And so this is a proof that multiplying equilibrium constants is appropriate when adding reactions. And that is it. That was a pretty short lesson. I suppose that makes up for that super long marathon 55-minute lesson that I did last unit.